machine here is something that we acquired, and we use this to do surgery on chips. And it's called a SIB, or focused ion beam machine. What this thing does is it draws down a narrow beam of gallium ions that you can use to image and also mill out stuff on the chip. So you can take a wire of interest and you can expose it. You can cut off the oxide, or you can cut it and burrow down past it. You can build up new wires. It's a pretty cool machine. Here's a gut. This is the column assembly here. This thing uses 50 kV to draw the beam, and then 30 kV to electrostatically focus it, and then some magnetics to raster it. But this is something that we never planned on doing, right? We just wanted to make a chip. But what happened is, when we first got the silicon back, it, of course, nothing works like you anticipate at first. So what we did is we got a little needle probing station, and hold on here, the camera's all messed up. And we used that to actually mechanically probe our chip. The trouble is, though, it was a very destructive process. So then I started learning about, what kind of diagnostic systems exist to actually do chip work. So I learned about these SIB machines, and back in Phoenix days, when we did the SX with them, they used a local company that would do SIB work for them, so that when they get the silicon back, now mind you, it takes like maybe 2 months when you submit your design, from when you submit your design to when you get the actual silicon back. So you get the chip back, apply power to it, and maybe it works for the most part, but there's something wrong. So what you do is you kind of do some, hypothetical scenarios like, what if, are we really generating this signal internally okay? Well, you can't see it. It's on a buried node. What you do is you send the chip off to a little SIB operator with one of these machines, and what he'll do is you have to tell him, he doesn't know anything about your design. You just have to give him a recipe, like, I want this cut, and I want this connected over here. So what he'll do is he'll do the surgery on the chip, and then you can, maybe bring an internal signal out to an external I/O pad that you can then easily, measure on an oscilloscope or something. And it's really invaluable for debugging chips. Now this machine, though, it's like a $3 million monstrosity, and it's got, we can't see, this one has all the cables troughed. There's like hundreds of cables that connect the control console out to the work chamber. This real high vacuum system. But this is not something I anticipated getting involved in at all, but kind of necessity required that we had some means to do these tests. And we were sending stuff off to a SIB company, but it's like it takes 48 hours to turn it around. You got to get your recipe ready, you pack up your chip, send it to them. They do the operation, they charge you $500, you get your chip back, and then, all that does usually is, well, okay, I see what's happening. Now I want to do another test. And so it just takes days, and then, like on the propeller, you just press F10, right? You can try your program over and over again. Well, if it took 2 days to try your program out, or worse yet, 2 months, you just lose your train of thought. You can't ever get anything done because you're so strung out trying to remember where it was you left off that it's very hard to make progress. So by getting our own SIB machine, I could do, four surgeries in 1 day, sequentially, and try out different ideas. So it really helps us focus in on problems and resolve them very quickly. And then it's pretty expensive, though, isn't it? $3 million? Oh, I'm sorry. Yeah. No, it's not expensive. I forgot to tell you this part. The thing is, new. I think Seagate used to own this machine. They probably spent about $3 million on it. But once this stuff comes onto the secondary market, once the initial customers are done with it, they move on to the next technology. Like right now, they're going to what are called back tools, where they work for the backside of the die. So this stuff's really expensive, and it takes a lot of work. You have to back grind your wafer. You just have to cut down to the area of interest, and then do your surgery. But the idea is that with potentially 13 metal layers on a chip, you may not be able to get to the signal of interest because it might be on layer, it might be 10 metals down and with no clear shot down to the signal of interest. So what they would do is do everything from the back side of the chip. So they mill down the wafer, and because on the very bottom level of the chip you've got all your transistors, and every connection has to at some point come to the bottom of the chip, right? Because that's where all of your active circuits are. But it's just a lot more complex. Now for us, this is adequate. So when the big guys get done with a machine like this, there's very little secondary market. We bought this machine for $30,000, which is only a penny on the dollar. And then had to spend about 6 months to learn how to, operate it. Well, not so much operate it, but get it to function like it's supposed to. And then it took another month or so of destroying it before I could successfully make a modification without actually burning something up. And this is only like. Go ahead.
Is that the machine where it's got the turbo vacuum pump?
Yeah, in fact, it's all, the skins are on it right now, but I'll show you what happens. This thing has 3 levels of vacuum pumping. There's a mechanical displacement pump, and then there is a turbo-molecular pump, which is like a turbine that spins at 40,000 RPM, and here's the one that's blown up. I don't know if you can see into here.
Yep.
Okay, so this thing was spinning at 40,000 RPM one weekend. I wasn't here when it happened, but it just kind of parked itself. And probably the bearings wore down, and once the blade started scraping against the interior, it probably wasn't more than a dozen revolutions before this thing just crunched. And this is all built out of 70-75 aluminum, so it's very hard stuff. But this is known in the industry as turbo salad. And these pumps, I think new, they're probably about $20,000, but we can get a used rebuilt for maybe about $3,000 or $2,000. So that type of pump is used to generate like about a 10 to the minus 6 torr vacuum level. But then locally, they need even more rarefication. So you see that thing that says Varian star cell? That's an ion pump. And the way that thing works is it has some soft titanium plates. They're kind of porous with permanent magnets on either side. And those plates are biased. There's about a 7 kV between the two sides. So what happens is if any gas wanders into that, it ionizes, kind of gets zapped and it ionizes, and then the positive and negatively charged particles separate and embed into those titanium plates. So in your whole life, that pump may never fill up. All it does is absorb, absorb, absorb.
That's cool.
So that's the fib machine. Any questions about that? Okay. There's another really cool machine here. So the fib machine lets you do surgery, right? But what if you want to look at your signals as the chip runs? What you need is an oscilloscope. So we could use the fib to cut down and bring up the test pad, right? We can build a big metal pad there that we could take a needle prober onto, and we could physically touch it with the needle. The trouble is, when you do that with very lightly driven internal nodes, which are completely adequate to drive to the next, 2 input gates or whatever, it can't survive going out onto a needle and a scope probe because that just swamps it out. It's too capacitive. So what you need is some special kind of way to be able to read signals on the chip without loading them down too much. So this machine right here, this is called an e-beam prober. There's 2 sections. This is the scanning electron microscope portion, so it has all the mechanical stuff in it. And then this is the control console, which has a lot of pump control in it, and also it has a Sun Microsystem computer that is used to manage the whole thing.